Hello, my name is Kirtana Mohan Rajan and I am going to explain my project for the class EEL 6509 Wireless Communications. My project is titled Diversity in Wireless Communication using Precoding and Multicast Scheduling and Resource Allocation for Orthogonal Frequency Division Multiple Access Systems. The need for multicast scheduling and resource allocation or MSRA in OFDMA systems or orthogonal frequency division multiple access systems has arisen due to the surge in large data rate requirements to support several users at the same time with a high quality of service and minimal rate loss. This has increased the need for applications that need to be transmitted to a selected group of users, creating a need for multicasting. Applications that it can be used for are weather information transmission, advertisements, etc. This multicasting enables resource allocation while maximizing spectral efficiency. Multimedia multicasting has several components. These include optimality and complexities, which are single rate based, enabling algorithms that are multi-rate based, MSRA fundamentals or multicast scheduling and resource allocation fundamentals, which include dealing with egocentric users and multicast group formation, multicasting in existing standards, challenges and problem definitions, as well as potential research opportunities. Now I will explain the different schemes for multicast scheduling and resource allocation or MSRA. The first scheme is predefined fixed default rate. This method is calculated to satisfy cell edge users who are likely to have low channel gains due to their poor channel performance. The second scheme is adaptive selection using least channel gain or LCG. Least channel gain is the transmission of data with the worst user's channel quality set as the group's default transmission rate. The third scheme for MSRA is dynamic transmission. This block diagram demonstrates CSI feedback that goes through the uplink control channel to the transmitter, which comprises of the subcarrier, bits, and power allocation block, along with the orthogonal frequency division multiple access modulation block. There is a downlink control channel or feedback path that goes to the user receiver, which has an OFDMA demodulation block that generates content requested by the user using the subcarrier selection and bits recovery block. However, multicast scheduling and resource allocation does have several challenges that I will briefly explain. These challenges are wireless channel dynamism, channel-aware resource allocation, multicast scheduling and resource allocation performance metrics, which include strict throughput maximization or STM, maximum minimum fairness or MMF, proportional throughput with fairness or PTF, and multicast group model. Wireless channel dynamism results from multiple and fast wireless channel variations, multipath propagation, and the diminishing of transmitted signals. Channel-aware resource allocation. Here, the channel condition does not change with every orthogonal frequency division multiple access transmission to prevent the allocation of resources during outdated channel state information. Now I will talk about the MSRA or multicast scheduling and performance metrics. The first is strict throughput maximization or STM. It is used where spectral efficiency needs to be optimized. It selects the user with the highest channel gain as the group's default transmission rate, which results in intra-group resource starvation. The second multicast scheduling and resource allocation performance metric challenge is maximum minimum fairness or MMF. It rectifies the fairness disadvantage in strict throughput maximization by giving priority to minimum users or groups to achieve their maximum rates possible. The third multicast scheduling and resource allocation performance metric is proportional throughput with fairness or PTF. The base station dynamically chooses the multicast group wherein the summation of log Tg for all multicast groups is exploited. The last multicast scheduling and resource allocation performance metric challenge is multicast group model. Here, the user's channel state information is considered at the base station to facilitate channel-aware multicast scheduling and resource allocation. The CSI is appraised at each user node and is transmitted to the base station's resource allocation block through the feedback path. Now I will explain the MATLAB codes for orthogonal frequency division, multiple access transmission and reception, and generate the following graphs for transmission and reception. This is the MATLAB code for orthogonal frequency division, multiple access transmission. I will now run the code to generate the graphs, the most important of which I have inserted in my PowerPoint presentation and my project report. I will now explain some of the graphs that I have inserted for OFDMA transmission in my presentation. This is a transmission characteristic of the Welsh power spectral density estimate. It has the power frequency on the x-axis versus the frequency in megahertz on the y-axis. These demonstrate the frequency responses of signal carriers at points B and C, which are demonstrated in the MATLAB code for OFDMA transmission. This is the Welsh power spectral density estimate with frequency in megahertz on the x-axis and the power or frequency on the y-axis at point D, which is again highlighted in the MATLAB code. Now I will demonstrate the MATLAB code for OFDMA reception. This is the orthogonal frequency division multiple access code for reception. I will now run it to demonstrate the graphs obtained, again the most important of which I have inserted in the presentation. This is the Welsh power spectral density estimate of the frequency response of the signal at point F, with the power frequency on the y-axis and the frequency in megahertz on the x-axis. This is the frequency response of this signal at point G. These are again variations of different signals at different points in the MATLAB program for OFDMA reception. This is the time response of the signal S of t at point E. A large number of orthogonal, overlapping, narrow band subchannels or subcarriers transmitted in parallel divide the available transmission bandwidth. The attraction of orthogonal frequency division multiple access is due to how the system handles the multipath interference at the receiver. This generates two effects: frequency selective fading and ISI. However, the main drawback with orthogonal frequency division multiple access is the large dynamic range of the signal. The conclusion of my project is that multimedia multicasting is one of the most common technologies for multimedia data transmission from one source to a group of users using a single transmission system. However, with increase in optimization, multimedia multicasting can provide better spectral resolution and can be enhanced to provide better services for the same. Thank you.